And now we're going to listen to Rainer Grimm telling us about concurrency improvements in C++20 in a deep dive. Really looking forward to this talk, Rainer.
So,
please take it away.
Hello.
Need to mute a bit. All right, let's go.
Okay, I start. Hello. Thanks for your words, Jens. Today I talk about C++20, but not about all what we have in C++20, only the concurrency stuff. And I do a deep dive. What do I mean here? The following. Only the red part here. Therefore, I will not talk about the big four, about core language and library improvements. I talk essentially about atomics, semaphores, ledgers and barriers, cooperative interruption, and finally about std/gthread. Okay. I will also talk a little bit about 11 or previous C++ standards to make in particular the picture complete, but you will see. Atomics. Okay, we have atomics since C++ 11. They are the foundation of the C++ memory model. Atomics, when you apply an operation on atomic, of course, this is atomic, but what is more important, they define synchronization ordering constraints. And the key part is that this synchronization ordering constraints will not only hold for atomics, but also for non-atomics. And this is the, let me say, other pillars of concurrency in C++. So these synchronization ordering constraints are used by the high-level threading interface, such as threads, tasks, mutexes, logs, condition variables, and so on. This is the important observation. All what we have, the synchronization we have with threading is based on atomics, and they also establish guarantees for non-atomics. So what kind of atomics do we have? Since C++11, we have atomic flag. It's extremely simple data type. It only supports two operations, clear, test and set. Clear puts it in a kind of false state. Test and set puts it in a kind of true state. And when you call test and set on atomic flag, it returns the old value in this same atomic operation. You see, when you read these two member functions, you can, for example, not get the value of atomic flag without changing it. You have to set it. But there's one extraordinary guarantee atomic flag provides. And this is the following one. This is the only data type which must be log-free. All the other atomics, to which I will come in a few seconds, can have internally a locking mechanism. Have a look. We have std/atomic, and std/atomic has a few partial and full specialization. You can specialize it for a pointer, for an integral type, for a user-defined type, for floating points, and for smart pointers. And this is, by the way, new with 20. But my point is the following. All of them can use under the hood unlocking mechanism. And so far, std/atomic smart pointer uses always unlocking mechanism. And this makes atomic flag special because it guarantees to be log-free. So what can we do with that? Atomic flag, of course, you can say test and set and clear. And for std/atomic, we have essentially the following operation. Is log-free, returns true or false, if it's log-free or not. You can load, store a value, you can exchange them. And these are the bread and butter operations of atomics. Compare, exchange weak, compare, exchange strong. I will ignore weak. But to make it complete, we also have fetch add, and plus equal, fetch sub, and minus equal. The difference between these both operations is that fetch add returns the old value, but plus equal the new value. And of course, we can increment, decrement. Now let me come back to compare, exchange, strong. This is I would say, the most important operation we have in atomics. This operation is also sometimes called a CAS operation, compare and swap. But here it's called compare, exchange, strong. I don't care. So this is how this looks like. You see, you have an atomic variable, atom. You say compare, exchange, strong on it. And it gets two arguments, expected and desired. Meaning, in one atomic operation, you compare atom with the expectation of the value atom should have. If both are equal, you in the same atomic operation update atom with desired and return true. When atom is not equal to expected, meaning the expectation of the atomic changed in the meantime, you update expected with the current value of atom in the same atomic operation, and you return false. Let me show you how this works in a simple example. Let me put it here. Here's a fetch mult. What is a fetch mult? This is an atomic multiplication. Of course, this program, there's no need for using an atomic, only for, let me say, to explain how it works. Here I have an atomic int. And now I want to multiply it by 5. You see it works. 5 goes to 25. But now is the interesting part. What happens here? Fetch mult. First of all, this is a function template. And what I use here is a concept to integral. So this is a function template. This function template takes this atomic by reference, because the caller wants to see this result, and the value it should be multiplied with. Then it stores the old value. You see, you load the value of shared load and you store it here. And now comes this compare, exchange, strong. Now, in one operation, you compare the value of shared with the old value of shared, then this one you got here. If they are equal, you in the same operation update it to old times mult, because you want to multiply, and you return true, meaning this while loop is done. If for some reason something happened in between here and there, and the value of old value changed in between, therefore short is not equal to old value anymore, you do nothing, but you change the value of old value to the current value of shared. You update your expectation, but you return false, meaning you do it once more, and you do it so long until this is successful. And how this looks like is a kind of an atomic transaction. You store the state of the world, and then you try optimistically to change it. When it works, you continue. When it does not work, you do it once more until you are successful. Because you have to imagine, would be typically a concurrent program. Therefore, you would there could be a lot of interleaving. And what you return here is the old value, because this is what fetch mult should do. It should return the old value. Okay, this was the atomic multiplication. Now we have, additional to fetch add and fetch sub, fetch mult. Okay, this was essentially, honestly, C++ 11 stuff. Let me jump 9 years further. We have atomic flag and stochastic. And what they essentially support in 20 is synchronization. On one atomic, you can say notify one or notify all. On the same atomic, you can wait. And now you will be notified by this either notify one or notify all. And here's the extremely interesting point. This atomic wait call blocks if atom is equal to while. This is an important observation. So let's say atomic is a Boolean. When this is false and this is also false, this call blocks. In case of true, not. Let me show you how you can use that. Let me go to the right and put it to the left. Here we are. This is a simple workflow. I have two threads. One is waiting for work. One is saying set data ready. So I have a producer-consumer workflow. Initially, I initialize my atomic bool to false, meaning this guy here has always to wait because atomic bool is false and false is equal to false. Therefore, this call blocks. It blocks until this guy, the producer, stores true inside. Now it has, and then afterwards notifies. Now it has true inside, and therefore this call will not block. And finally, waiting for work can add 2 to the index position 1. And now we have a synchronization on a non-atomic because my shared work is just a vector. And we have the synchronization based on atomic bool. Okay, let me jump back. I will come back to this example in a few seconds. Okay, with C++20, we also have atomic shared putter, atomic weak putter. Let me put it this way. One of my favorite quotes from Tony van Eert: forget what you learned in kindergarten. Don't share. And shared pointer makes this wrong by design. It's shared. And when you share, you have to synchronize, you have to protect, you have to be aware of data races. But the question is a shared pointer thread safe? Kind of. Once more, I'm only talking about 11. Kind of. The control block, the handling of this resource is thread safe, but not the resource. And therefore we got with C++20 atomic shared putter, atomic weak pointer. And to repeat it once more, both of them are currently always implemented with a locking mechanism. They are called atomic, but under the hood they use a locking mechanism, which is fine from the standards point of view. You might ask yourself, or let me put it differently. Here's the reasoning from help from a paper. Why do we need atomics or atomic shared pointer, atomic weak pointer? First of all, out of consistency. You may not be aware of it, but stud shared pointer was in 11 the only non-atomic data type on which you could apply atomic operations such as load, store, exchange, and you know what. And this was inconsistent. Therefore, now it's consistent. We need an explicit atomic shared pointer out of correctness reasons. You see, in C++11, you have to do it this way. When you want to store something in a shared pointer in an atomic way, you have to use this function atomic store. But you can easily forget it, and then you do this one, and you have a data race. Therefore, we need this for correctness. And the third argument is, we could also make the shared pointer by design in 20 thread safe. But this would be a pessimization because you often want to use the shared pointer in a single threaded environment, and here using a lock would be an overkill. Okay, and this would break the general or the meta rule in C++. I don't have it exactly in my head. Only pay for what you use. We have a new atomic data type in C++20. This is atomic ref. And this applies atomic operation to the referenced object. You see, ref. Meaning reading and writing of this reference object is no data race. Of course, you have a reference. From the ownership semantics point of view, you must guarantee that the thing you reference lives long enough. And std atomic ref provides essentially the same interface such as std atomic. Have a look, such as this stuff here. It has almost the same specializations such as std atomic, with one exception. We don't have std atomic ref of smart pointers because we don't need them. Okay, let me show you an example. Here we are. Let me start here. Here I have an expensive to copy object. Sorry, it's not expensive to copy, but I have to start my story. You see, expensive to copy. And then I invoke the function count. And afterwards, I return the counter, which is now 1537. And let me see what's happening here. In particular, count. This is the function count. It gets this expensive to copy thing. And now here's the interesting part. I create an atomic ref around this counter inside this exp. And this is, of course, not thread safe. You see, this is an int. But because I use it in atomic ref, is thread safe. Because now also this count is thread safe. And here I do the interesting stuff. I create 10 threads. You see, in vector of thread, I create 10 threads. Each take the counter by reference. Then I create a random number between 100 and 200. And I add that amount of values to this shared I. Sorry, to this shared counter. This is just the running variable. So I added to this shared counter. And this counter is the counter here, which is atomic ref. And this is thread safe. I cannot prove it, but I can give you a strong hint. When I use fsanitize to detect data races, it will not become red. Let's wait for a few seconds. Sanitis, the S is missing. Still running, you see. You see nothing, which is good, sorry. But when I make this here a non-atomic, you will see in a few seconds, this looks not so nice anymore. Still running. It's red. Thread sanitizer detects a data race. And this data race is in line, let me show you that. 28 is this line. Oh, here we are. This is this line. And of course, it's the counter. Because this is local and this is local. Okay. Let's go on. We have in C++ 20 semaphores. They are synchronization mechanisms to control access to a shared variable. A semaphore is initialized with a counter greater than 0. Requesting a semaphore decrements the counter, releasing the semaphore increments the counter. A requesting thread is blocked if the counter is bigger than 0. Sorry, if the counter is 0. Sorry, this was a mistake. We have two kinds of the semaphores. essentially we have one loop. We have a counting semaphore and a full specialization for one, which is called a binary semaphore. And a binary semaphore behaves pretty similar, such as a mutex, because it can have only the values 0 and 1. And for a mutex, you can think about, okay, unlock is 0, log is 1. So you can switch back, forwards and back between 0 and 1. Okay, once more. I would see this as a, let me say, a generalization of a mutex. But there's one key difference between a semaphore and a mutex. A mutex must be locked and unlocked in the same thread, but not a semaphore. You can lock it, not lock it. You can acquire it in one thread and release it in another. This is the main difference. Okay, this is the interface of a semaphore. You can ask the maximum value the counter could have. You can release the semaphore, and by default, you update the counter by 1. You can acquire it. Acquire means you decrease the count by 1, and this call blocks if the count is 0. And then you can do it. You can try to do it. Try acquire for, try acquire until. Try acquire means you try to acquire it. If the semaphore, if the count is bigger than 0, you get it. When the counter is 0, you will of course not get it, but you will also not block. You just try to get it. And you can also do it with a time duration and a time point. These are entities from C++11. Once more, this is a time duration. This is a time point. And here you try to acquire it for a time duration or until a time point. Okay, let me show you an example. The same workflow such as before, exactly the same. I have waiting for work, I have set data ready. And here is my non-atomic variable, just a vector, which I fill partially in the set data ready function and which I put in the rest of it in the waiting for work function. And here's the semaphore, a counting semaphore. It starts with 0, meaning it blocks, and it can at most have the value 1. Therefore, it can flip between 0 and 1. Meaning the guy waiting for work, this guy here, cannot get it because it has the value 0. It can only have it if this guy here releases it. With this release call, the counter goes from 0 to 1, and therefore this guy can have it. So you see, this is, I would say, a pretty easy to read and pretty easy to use synchronization between threads. Okay, and let me jump back. Now to my favorites. We have various ways in C++ to synchronize threads. I will show you a few additional examples in a few seconds. In 11, you essentially, when you want to synchronize more than once, you only have one way to do it, one possibility, and this is to use a condition variable. When you have only a one-time synchronization, please use a future promise pair. But here, I want to do it more than once. So I have a condition variable. A condition variable has two functions to notify 1, notify all. With notify 1, one of the waiter is notified, with all of them. On the opposite side, we have the waiting guys. Wait for, wait until. This guy waits without a condition, without a time condition. This 4 waits with additional time duration, in this one with additional time point. And now let me talk about the fun. I'm not a big fan of condition rebels. Let me talk about the fun. Condition rebels can be victims to extremely ugly phenomena, and this is spurious wake up and lost wake up. Let me tell you a story, and then I say this is how they work. Imagine you lay in bed, you sleep, and you wait for the alarm clock to go. This is your notification. And then for some strange reason, you are woken, but it was not the alarm clock. It was the cat scratching at the door. What can you do? When you are in bed, you have to check something which happened immediately before the notification. And this check is what these 3 dots here represent. I will explain it in an example in a few seconds even better. So what you essentially check here is how late is it, for example? Once more, I was in the picture, you lay in bed. This is a spurious wake up. The waker can be awoken, but it was not a notify one call or notify all call. And then we have the lost wake up thing. Lost wake up means you go to bed after the alarm clock went. And this is a lost wake up, which means under a deadlock, because you wait for an event which will never happen once more. Because the standard says only when the waiter, the thread executing this wait function, is in the wait state, it will recognize a notify one or notify all call. If not, you have a lost wake up. Let me describe it to you once more. I want to explain it because you immediately see that this is pretty complicated to make right. Here's a single producer, single consumer workflow. Someone prepares the work, someone consumes the work. Let me describe this workflow. And I have to say, this is executed in one separate thread, this in some other thread. And let me describe this workflow from the point of view of the waiter. So here. First of all, you call log on the mutex. Then when this mutex is logged, you go into the wait call. And first you check now if return ready is set. Return ready is something, in this case here, which happened before the notification. Meaning when the return ready is set, you know that this already happened. Therefore, you know this was the right notification. When your return ready is not set, this so far didn't happen, meaning this was a spurious wake up, the cat scratching at the door, for example. Then after this check, so assume return ready is not set, meaning false. This means you immediately release the lock and go into the kernel modus and sleep. Then you sleep. Then at one point you get a notification. Now you check once more. Is this a spurious wake up or not? When your return ready is set, you know this was not a spurious wake up. When your return ready is set, you know this was the cat scratching at the door. Let's continue. Now in one point in the future, you get a new notification. And now return ready is set. Therefore, this event happened before. Therefore, you know, okay, this is my time. I can continue here. You complete your work, and exactly here, when this lock goes out of scope, you release it. I'm not sure if you recognized it, that I made a small mistake in my first sentences. Once more, when you are the first time here, you check if return ready is set. When return ready is set here, you know that this ready true already happened. And this means the alarm clock went before you are in the bed. And this is how you protect yourself against a lost wake up. Once more, a lost wake up. Okay, let me show this to you live. Okay. I have the same workflow such as before, but now it's a little bit more complicated, but essentially the same workflow. Okay. Waiting for work, set out already. Now let's check here. Waiting for work waits here, you see, while holding lock. And here the lock is released. Set data ready, as in my example, sets here data ready to true. Initially it's false, sets data ready to true, and sets afterwards notification. This call notify one is thread safe, therefore you don't have to protect it. But of course you have to protect this data ready. Therefore I have here two critical sections. Okay, so far is fine. Let me do it once more. Always when the worker happens or is executed before the sender, this is fine. This means you are first in bed before you got a signal. But when the sender comes first, the alarm clock goes before you go to bed. This means a lost wake up. Let me try to provoke it. Now I remove, you see, I remove the additional predicate. And therefore now I'm a victim of lost wake ups. So far is fine. Let me do it a few times. I hope I have a little bit of luck here. Now I'm out of luck. Maybe I change the order here, which may increase the probability that I get an issue. Go on, go on. Looks good. This is a timeout. I have a timeout. You see, processing time exceeded. Meaning I had a deadlock, and in this compiler explorer, this was a denial of service attack. And now you see, I executed once more, now it works. So essentially it's a 50-50 chance that you get a deadlock when you do it the way such as I did it here. Okay. And now I have a play. I want to make a play. And I call, or a game. And I call this game, let me see it. I call this game ping pong. And I do it in different ways because honestly, I love it. When I can do one workflow in more than one way. I try to implement it in various ways, and then I answer two questions. First question, what's the easiest way to implement it? And second, what's the fastest way? And this is my game. One thread executes a ping function and the other a pong function. The ping thread The ping thread is a thread performing the ping function. The ping thread waits for the notification of the pong thread and sends the notification back to the pong thread. So we have always ping, pong, ping, pong, ping, pong. And this game ends after 1 million ball changes. Let me now show you a few implementations. Here I use a condition variable, but honestly, I cannot do it with 1 million calls. I can only do it with 1,000 calls because this takes too long. And now you see 1,000 ball exchanges take around, 1/100th of a second. And here's how this game goes. I have two condition variables, 1 and 2. I have two threads, one performing ping, one performing pong. I end this game after count limit, and count limit in this case is 1,000. In the final numbers, it's 1 million. And this is what the ping guy does. It uses a unique lock, and then it waits. It waits while holding the lock until this predicate is fulfilled. That ready is equal to false. When this is false, it puts it back to true and uses the other condition variable to send a notification to the other thread. And the other thread is exactly waiting on this condition variable. You see, 2 is notifying, and here 2 waiting. 1 is waiting, and 1 is notifying. So it's a back and forth. Essentially, this is the same code such as here, but let me say anti-symmetrical. I hope you know what I mean. And here I increment the counter because I want to end at 1 million, in this case only 1,000 ball changes. Okay, this is how I have done it with condition variables. And I have measured the time. Let me go to the next example. Let me use an atomic flag. I'm way slower, but the reason is I did 1 million ball exchanges, you see? Now I do it with 1 million. And this is how I do it with an atomic flag. I have an atomic flag which has initially the state false. Meaning, here I put it to true, you see? True. And now it has the state true. Meaning, true meaning this guy can continue because this guy blocks on false. But of course, here it has the value true. Then it clears it, it puts it to false and notifies. And this guy does exactly the opposite. It blocks on true, sets it to false, once more, this blocks on true, meaning when this passes, it's false. Therefore, I set it here to true, increment the counter, and then I notify. Okay, this was the workflow with atomic flag. The workflow with atomic bool looks honestly pretty similar. I have one atomic bool, initially set to false. Here I set it to true, meaning this guy can start because this guy blocks on false. Then I store false in it and notify. And here I block on true and set it true. You see, also kind of symmetrical. Finally, I come to semaphores. I use two semaphores, both initialized with 0, but both can have also the value 1. And this is how it works. I first release signal to ping. Now signal to ping goes from 0 to 1, meaning this guy can acquire it. Then it increases the counter, then it releases the other. And now this guy can acquire it and releases the other. And so it goes forward backwards. Now the interesting question, we have two questions to answer. Which one is the nicest to implement or to consume implementation? I'm not 100% sure. I only know that I think this one is the complicated implementation. And then I would say atomic bool or semaphores are the nicest one. But this is a matter of taste. But it's pretty clear this is the by far most complicated one because you have to use a predicate. Okay, let me jump back. And here are the numbers. Please don't compare this both. This is a Windows PC and this is a virtualized Linux. But what you can see here is it's pretty obvious. Condition wrappers is terribly slow on Linux and slow on Windows. And what astonished me really was how fast our semaphores are. They are in the ballparks of atomics. And of course, way easier to use. So in C++20, I strongly suggest that you don't use condition wrappers. Let me talk about another synchronization mechanism, latches and barriers. A latch is useful for managing one task by multiple threads. When you have a latch, let me put it this way. You initialize a latch with a counter, and all have to wait until the counter becomes 0. So it's kind of the opposite to a semaphore. So latch countdown. Which countdown? You count down by 1. But you will not block if the countdown, if the latch becomes 0. With try and wait, you return 2 if the counter is 0. With wait, you block if the counter is 0. Sorry, you block if the counter is not 0. I hope I made no error. Once more, this only blocks when the counter is bigger than 0. Meaning here you block if the counter is bigger than 0. And arrive and wait makes both in one step. It counts down and it eventually blocks. Essentially, it's a countdown and wait call. By default, you count down by 1, but you can also provide a bigger value. And here's a simple workflow. I synchronized standard cout in an ugly way. I will show it to you in a more nice way in a few seconds. Have a look here. I have 6 workers. Herb, Scott, Bjarne, Andrew, and finally David. All perform the same work. And this is what they have to perform. This is a function object. They write their name out and then work done. Then they say arrive and wait. Meaning here, they decrement the counter by 1 and block or wait if the counter is bigger than 0. And of course, initially the counter is 6 and I have 6 threads. Meaning all wait here until the counter becomes 0 and then they say see you tomorrow. And this is the reason why we have such a nice output here. First, all 6 prepare their work and then they say see you tomorrow. This is a latch. But we have also a barrier. It's pretty similar, such as a latch, but a barrier can do one thing. A barrier can be used more than once, a latch only once. So we have an arrive call, which atomically decrements the counter by update. We have a wait call, which blocks when the counter is not 0. or to be specific, until the completion step is done, I will say a few words about completion step. Then we have arrive and wait, which is equivalent to arrive and then wait. And this is pretty interesting. We have arrive and drop. This means with arrive, you count down, but drop is special. Here you say, in the next iteration, I want to be out of this game. Meaning for the next iteration, by default, you have the same counter. So you initialize with 5. The next iteration, it stays 5. But with arrive and drop, you go down to 4. And I said something about completion step. You can invoke a barrier with created with a callable. And this callable runs when the counter becomes 0. And this is the so-called completion step. And when this completion step is done, the second iteration, if required, will come, or the next iteration. Let me show it to you. Here I have, let me see it, a more elaborate workflow. I have 3 full-time workers and 3 part-time workers. And I have a barrier with the value 6. The part-time worker, and I have 2 work packages, one at the morning, one at the afternoon. But the part-time worker will only work in the morning session. And then when they are done, they say arrive and drop. Meaning initially the counter is 6. They count down here by 3, and here by 3 makes in sum 6. But in the afternoon session, only the full-time worker will be working. Meaning here they call once more arrive and wait. But here the counter is not 6. It's 6 minus 3, 3. You see here I have 2 iterations. 1, 2. And to do that, you need a barrier. Okay. Now I come to cooperative interruption. First of all, why it's a bad idea to kill a thread? You don't know in which state the thread is. Maybe the thread is not done with its work. Maybe the thread is in a critical section. This would mean you could have a deadlock. Therefore, we don't allow it to kill threads. We only allow cooperative interruption, meaning you can send a signal to a thread, and now this thread can react to it, and you can only do it once. And this feature is built into gthread. This is the improved stud thread, and into stud condition variable any. I emphasize it once more, any. This is a generalization condition variable, a generalized condition variable. And this functionality consists essentially of 2 parts. We have a stop token, which can ask if it has an associated stop state, or if a stop was requested. You can only request a stop once. On the other side, we have the stop source. This is the guy sending the stop signal. With this get token call, you create the stop token out of a stop source. With stop possible, you ask if source can be requested to stop. With stop requested, this is true. If stop possible and request stop was already called. And this request stop is this request to stop, or this signal. Let me show you an example. In this case, using the gthread. The next example is more sophisticated. By the way, this is red because I use standard CR, the error channel. Okay, let's see what's happening here. I have a little bit of interleaving, which is not bad. Anyway. Okay, I have 2 threads, G thread, non-interruptible, interruptible. And this interruptible got here an additional argument, a stop token. A stop token is pretty easy, pretty cheap to copy. It got a stop token. And because it has this stop token, it cannot use it here to ask if a stop was requested. This is cooperative interruption. And both threads count up to 10 and sleep for 1/5 of a second. And then they display non-interruptible, interruptible. And this is how it starts. You see, interruptible, non-interruptible, interruptible, non-interruptible. And here it stops. Why? Because in the main thread, after the main slept for 1 second, in the main thread says request to stop on both threads. But only the interruptible thread reacts. And therefore, this thread here, where is it here? Reacts to it and does it by returning. And this means only the non-interruptible thread continues. This was cooperative interruption, how you can use it with a G thread. Honestly, when I studied C++20, a little bit disappointed because I thought, okay, it's a fine feature, but we could imagine more. But then I recognized you can do way more. Stop source and stop token are general mechanisms for sending a signal. You can essentially cooperatively interrupt any running entity. Let me show you an example. And I will use also now a stop callback. You will see in a few seconds. Let me start here. I have a stop source. Then I create out of this stop source a stop token. And now I copy this stop token in different entities. You see a thread, a G thread, a promise, exactly as to the sync. Here a promise. Where's my promise? Here's my promise. And I also do something here locally. Let's see what std_thread is doing. Std_thread performs this function, gets the stop token and its name. And this is what std_thread is doing. Function 1. Here's function 1. Stop token and the string. And this is the interesting part. It sleeps for 1 second. And now what I do here is I ask for stop requested. After 1 second. I have to apologize. The interesting part will come here. I can also do it with a G thread. So I can also use function 1 in a G thread. I can use my stop token as std async, you see? Stop, and here I asked if a stop was requested. But now comes the interesting part. Here I have a promise, which returns void, meaning nothing. Then I create a future out of this promise. And now I execute function 2. Function 2 gets a promise by R value because you cannot copy a promise. You can only move it. And the stop token. And let's see what the function 2 is doing. It sleeps for 1 second. And here, this is the interesting part. Here, I register a callback. Meaning, when some stop request happens, I will just say stop requested. You can register callbacks. Not one, an arbitrary number of callbacks. You don't have the guarantee in which order they are performed, but you have the guarantee that they are performed in general. And here I register the callback. And at the end, you see it here, I say request stop. And I also ask in the main thread if a stop was requested. See, I can also ask for it in the main thread. And here are all the entities which I friendly ask to stop. And now you see this is a pretty generic mechanism to cooperatively interrupt any running entity. But once more, you can only do it once. You can only say once, request stop. Now to the last point. Oh, almost. This is only a small thing. You know, this issue we had with std thread. When you have a thread, and you forget to join it, and this thread T goes out of scope, and it's still joinable, meaning no neither called join nor attach on it, in the distractor of T, std terminate is called, which causes the abortion of the program. And this is the error message you get. Terminate call is an active exception. How can you overcome this issue? Pretty easy, just use a G thread instead of a thread. Now you see it works. Because a G thread automatically joins in its destructor if necessary. A G thread models RAII. Resource acquisition is initialization. Because in case you call, you join automatically in its destructor. Okay, this was a small feature, but a nice feature. But now to the last feature, we have synchronized output streams, and I see I'm good in time. And they allow you to write an entire, let me put it this way, an entire sentence in atomically to an output stream. Let me show you an example. Here I have, you see, std async stream, which is a wrapper around standard cout. And all what I put here on site, nothing would happen. Even this std endl call, which will usually flush the buffer, will not have any effect. The output is written in an atomic step when this guy here goes out of scope, and this is exactly here. And this is, once more, RAII modeled. Because this is what you do when you go out of scope. You synchronize the output stream, or you flush the output. And you can also do it here with a temporary. And you see, I create a temporary to standard cout. This temporary goes out of scope exactly here. And therefore here, all is written in one atomic step without interleaving. Finally, here's the program. I have this is, by the way, from CP reference, and wrapper around standard cout. It says hello world at the end. Why at the end? Because this guy goes here out of scope, and then the output is flushed. And here in between, I get a reference to it and write it here in an atomic step. And therefore, we got here inside goodbye planet. And afterwards, when bout1 goes out of scope, hello world. And now I'm done. I only talked about this red part in my timeline about atomics, which were improved with C++20 in particular. Once more, you can wait and notify, synchronize with them. We have now atomics for floating points and for smart pointers. and we have atomic ref. We got additional semaphores, which blocks when the counter becomes 0, latches and barriers, which blocks when the counter is not 0, cooperative interruption, and finally stud gsud. Thanks a lot. This was it.
Thank you, Rainer. That was a very interesting presentation. I enjoyed it a lot.